Hello everyone, this is Dr. Lennon, and today we're going to look at dividing polynomials. So we're going to look at two ways. We're going to look at synthetic division, which is a shortcut that works in some special cases, but it's really nice because it's really fast. And then we're also going to look at traditional long division with polynomials. So let's start with the synthetic division example. So synthetic division. This is a shortcut method that works when you're dividing by a polynomial of the form x minus a constant. So this is a quick method when we divide by x minus c. And we only pay attention to the coefficients. And one reason this is really important, and why it's, you say, well, x minus c doesn't represent very many polynomials, but it does give us a way to test whether the number c itself is a root of the polynomial. So if the remainder is 0, then let's say then x equals c is a root of the numerator polynomial, or the polynomial that we're dividing into. This is essentially just a restatement of what the factor theorem says. So this is kind of a simplification of the factor theorem. So that's another thing we can say there. This is just the factor theorem if you want to look that up. So let's actually look at an example where we go ahead and do this. So we'll look at quite a few, but they're really pretty basic. Like I said, we're only paying attention to the coefficients. So perform each division. And for this example, they're all going to be synthetic divisions. So A, we want to do 2x cubed minus 7x squared plus 5 by, or we'll say divided by, so sometimes we'll put these in parentheses. There's a variety of ways that this can be written, but divided by x minus 3. So the way I like to write my synthetic divisions is in the upper corner you'll write the root. So the root would be the number that would make the denominator polynomial 0 if you plug it in for x. So in this case it would be 3, because 3 minus 3 is 0. So we'd have 3 in this corner. And then we write the other numbers from the largest degree to the smallest degree. So the coefficients would be 2, negative 7. And now notice that there's no x term. It goes from minus 7x squared to 5. So I'm going to put a 0 there because we can think of there as being maybe a plus 0x between the negative 7 and the 5. And then we have 5 here. And so then we draw a line. And what we do is we bring the first number down. So that's a 2. Then we multiply 2 by this number in the corner up here. 2 times 3 would make 6. And then we add. So negative 7 plus 6 would be minus 1. And then I take that negative 1 and I multiply it by the number on top again. So negative 1 times 3 is minus 3. I add 0 and minus 3. I get minus 3. Then I multiply these two, and I get negative 9. 5 plus negative 9 is negative 4. So this is your remainder term. And then each of the other terms are going to go according to the typical degree. So this is going to be degree 0. This is going to be degree 1. And this is going to be degree 2. So basically what that means is if you rewrite that division, it's telling us that if you do 2x cubed minus 7x squared plus 5 and you divide it by the x minus 3 as we did, the result is that you get a 2x squared minus x minus 3, and then you have your remainder of minus 4 with your leftover x minus 3. So that's the fraction left over because x minus 3 could not go into the remainder of minus 4. So that is the division. So you have your polynomial, and then you have your remainder part if the remainder is non-zero. If the remainder happens to be 0, then that means, again, the polynomial goes in cleanly, and you don't have any of that to worry about. So let's go ahead and do one more, and then we'll talk about how this can apply to figure out either the if something's a factor or if it's a quotient. So let's go ahead and do another synthetic division. Let's say we have, so did I list this as part A? Sure did. So that's the end of this example, and then we'll start part B. So let's say we have, let's say x cubed plus 2x squared plus 2x plus 1, and this is going to be divided by x plus 2. And then just as before, we have so now it's going to be a negative 2 in the corner. Negative 2 plus 2 would make 0, and I'm getting that from looking at the x plus 2 polynomial that I'm dividing by. And then on top, I would list the coefficients, 1, 2, 2, and 1. Notice nothing's missing here, so I don't really have any issues. So the first step is always just bring the number down, and then after that, that's when we start multiplying and putting them on top of the next one. So I do negative 2 times 1, which gives me negative 2. I add those together and I get 0. So 0 times negative 2 is again 0. Then I can add, I get a 2 there. 2 times negative 2 would make negative 4. And then I add those and I get a negative 3. So in this case, what happens, well, I've got my x cubed plus 2x squared plus 2x plus 1. And when I divide it by this x plus 2, I'm really getting what? Well, this is degree 2, 0, degree 2, degree 1, 0, and then the remainder. So that's telling me I have an x squared plus a 2, and then plus this remainder of negative 3 divided by x plus 2. And that is the polynomial division there. So I've talked about the factor theorem already. So let's go ahead and kind of talk about the two theorems that apply with this synthetic division kind of naturally. So there's two. There's the remainder theorem and the factor theorem. So the remainder theorem is, I suppose, a bit more general. So what does the remainder theorem say? It says if a polynomial p of x is divided by x minus c, which is what we've been doing with all of these synthetic divisions, then the remainder is the same thing as plugging c into the function there. So that's not too hard to show. Right, I mean, a quick sketch of the proof is just if you have p of x is equal to some x minus c polynomial times your quotient plus the remainder. If you plug in c into this polynomial, you would end up with c minus c times q of c plus the remainder, and we see that the value c plugged in is actually just equal to the remainder. So fairly quick proof there. And for that very fact, we can see that if the factor theorem is going to say that we know that c is a 0 if and only if x minus c is a factor, right? So if you have c being a 0, that would mean there's no remainder, right? And if there's no remainder, then p of x can just be written as x minus c times the quotient polynomial with no remainder. So the factor theorem follows directly from this one. So again, you don't really need to know the proofs of any of these things. You just need to know how to apply them. But basically c is a 0 of p of x if and only if x minus c is a factor of p of x. So we can do a couple quick examples that utilize these theorems combined with synthetic division. So let's say, let's go ahead and let p of x equal, let's say 3x to the 5th plus 5x to the 4th minus 4x cubed plus 7x plus 3. So let's go ahead and say so let's use the remainder theorem to find the value of, let's say, p of minus 2. So again, the remainder theorem is just saying if we're doing p of minus 2, that's the same thing if we want to use synthetic division as figuring out what the remainder is when you divide by x minus negative 2 or x plus 2. So from the remainder theorem, p of minus 2 is the remainder when p of x is divided by x plus 2. So that's what we're going to do. We're going to use synthetic division to go ahead and just figure that out. So again, we would put minus 2 in the top left corner and then list our coefficients. 3, 5, negative 4. We don't have an x squared term here, so we need to put a 0 there. We have a 7 for the x and then a 3. So again, this is quite long in terms of synthetic division number of steps. We've got a lot of terms, but the process just keeps going. So bring the 3 down, start there, then multiply by negative 2 and put that below the 5. So we get negative 6. Add, we end up with minus 1. Take this minus 1, multiply by the negative 2, and then write that result, which is positive 2, below the negative 4. Then we do negative 4 plus 2, which comes out to negative 2. We multiply negative 2 with a negative 2 in the top left corner. We get a positive 4, write that below the 0. Add those two, we get a 4. Take that 4, multiply by negative 2. We get a negative 8, not negative 6. We get negative 8, we write below the 7. Add, and we get negative 1. Negative 1 times negative 2 is positive 2. Add, and we get 5. So we get quite a lot of terms, but again, we're not looking for the polynomial. We're just looking for this number. That remainder is going to be our answer. So hence, we know that p of negative 2 is equal to 5. And what you could do is you could go ahead and plug it in the traditional way. Go ahead and replace all the x's in the p of x formula by negative 2 in parentheses and evaluate that, and you should get the answer of 5 as well. So if we were doing that by hand, that might be a little bit more involved than what we were doing here. So let's go ahead and look at how we might apply the factor theorem. The factor theorem is the same thing. We're just essentially trying to show that if the remainder happens to be 0, then it's a factorization for the polynomial. So use the factor theorem to show that x equals 1 is a root of p of x equals x cubed minus 7x plus 6. So basically, if we divide by x minus 1 and show the remainder is 0, then x equals 1 must be a root by the factor theorem. So let's go ahead and do that. So we can put a 1 in this top left corner, and then we have our 1 from the x cubed. There's no x squared term, so we put a 0, a minus 7 from the minus 7x, and then a 6. So we want to go ahead and perform this division. So we bring the 1 down, multiply, we get 1. Add, we get 1. Multiply 1 with 1. And then we add, we get negative 6 here, and then we get a remainder of 0. So by the factor theorem, x equals 1 is a root of p of x. Even better than that, it actually tells you how it factors, right? So if you take that p of x, x cubed minus 7x plus 6, it actually factors into exactly the thing you were dividing by, the x minus 1 times that result we have up here, right? The remainder is 0. Our degree 2 term is x squared. Then we have an x, and then we have a constant term of minus 6. So it's going to be x minus 1 times x squared plus x minus 6. And that's actually the factorization. And then if you wanted to go ahead and go one step further, x squared plus x minus 6 is a quadratic that you should know how to factor. So you could actually go ahead and find all the roots of that degree 3 polynomial. Okay, so that's pretty much it for the synthetic division. Let's talk about the polynomial long division. That's going to work kind of like long division from that we did with integers in grade school, where we're kind of focusing on each degree as if it's a place in a long number. But we can't just pay attention to the coefficients like we did for long division. So writing out the entire algorithm is, in my opinion, not something that is all that useful because it's a little abstract. It's better to just kind of look at a couple of examples, but mostly for what we're looking at with polynomials in terms of finding roots and things like that, synthetic division is going to be our primary tool, but I thought I'd show you just a couple of examples of long division. General polynomial long division. So we have to pay more attention to matching the coefficients directly. So let's just look at some examples. So what we want to do here is let's go ahead and divide, let's say 8x to the 4th plus 6x squared minus 3x plus 1 by 2x squared minus x plus 2. So we set this up kind of in the old format. We take the 8x to the 4th, and again, we want to keep track of all the places, whether or not there's a degree, whether or not that degree term appears. So in the first polynomial that we're dividing into, 8x to the 4th, there's no x cubed term, but we're going to go ahead and account for that by adding a 0x to the 3rd term, so things line up when we go ahead and actually perform the polynomial long division. So we've got this 8x to the fourth plus 0x cubed plus 6x squared minus 3x plus 1, and we want to divide by 2x squared minus x plus 2. Now, the thing is, we really only have to worry about the leading terms that we have. So this 2x squared, I just need to divide it into 8x to the fourth. And we're just kind of eliminating all of those leading terms as we go down the list. So what can I multiply 2x squared by to get 8x to the fourth? Well, that's going to be 4x squared. So if I do a 4x squared, I know 4x squared times 2x squared is going to give me an 8x to the fourth. But then I need to continue. I'm not just multiplying the leading term, I'm actually multiplying each of the terms and then accounting for those as well. So minus x times 4x squared is going to be minus 4x cubed. And then plus 2 times 4x squared is plus 8x squared. So I'm actually taking this quantity and I'm subtracting this entire quantity from the polynomial above it. So 8x to the fourth minus 8x to the fourth, those cancel and you just get 0. 0x cubed. Then I've got minus 4x cubed, and I also have another negative from outside the parentheses. That's going to leave me with 4x cubed. And then I want to do 6x squared minus 8x squared, and I have minus 2x squared. So again, since I'm going to expect 3 terms, I want to bring down my next term as well, the minus 3x. And now this is what I'm trying to eliminate. Again, I'm looking at my 2x squared from the divisor and the remaining leading term, 4x cubed, down on the very bottom. And I know that if I multiply by if I multiply 2x squared by plus 2x, I'll have 4x cubed again, and I will be able to eliminate that first term. So I take the 2x and I multiply through by each one. I get a 4x cubed, and then 2x times minus x is minus 2x squared, and then 2x times plus 2 is plus 4x. And then I want to go ahead and subtract all of that. And when I subtract, since the first 2 terms match, they both cancel out. I get 4x cubed minus 4x cubed, and then minus 2x squared plus 2x squared when I distribute the negative. And then I'm going to have a minus 3x minus a 4x. So that's going to be minus 7x. And I can bring down that plus 1. And now there's nothing else I can do because my leading term of the divisor 2x squared is degree 2, and the term left over is just minus 7x. So that tells me that actually, when I do the division here, the 8x to the fourth plus 6x squared minus 3x plus 1 divided by 2x squared minus x plus 2, I'm going to get exactly 4x squared plus 2x, and then I have my remainder, which is the minus 7x plus 1 divided by 2x squared minus x plus 2. It's exactly like when you're dividing, numbers. If you were to say divide 15 by 7, it would go in 2 times, and then you would have 1 left over. So if you do 15 over 7 as a mixed number, that's 15. So let me just write that down. So to liken it to this part, 15 over 7 is essentially like 2 plus 1 over 7. Because if you do 15, if you do the 7 into the 15, that goes in twice, and you would take away 14, and then that would leave you with a remainder of 1. So that's where that comes from. So note the analogy that we're seeing between division by integers, traditional long division, and these division by polynomials. So rather than the places being what we're focusing on, now we're focusing on the exponents of the variable x. All right, so let's do one more long division example, and we'll leave it there. So let's go ahead and do one more example. So we'll just say find the quotient and remainder using long division. So let's go ahead and do 9x squared minus x plus 5 well, this is a very short example, it looks like, but we'll see what happens. Divided by 3x squared minus 7x. There's really not much to this because the degrees match, so there's really only one step you can do. So maybe this wasn't the best example. But anyway, so we have the 9x squared minus x plus 5, and then into that we're dividing 3x squared minus 7x. Again, I'm just trying to match the 3x squared into the 9x squared, and I can do that by multiplying by 3, and I would have 9x squared minus 21x, and then I subtract, and I have the 9x squareds will cancel, then I'll have minus x plus 21, so that would give me a positive 20x plus a 5, and then I'm already done, so that's actually just the remainder, because the degree of 3x squared minus 7x is 2, and the degree of the remainder is 1, and once the degree of the remainder is smaller than the degree of what you're dividing by, then the division process ends. So that tells me that my 9x squared minus x plus 5 over 3x squared minus 7x is just 3 with that remainder of 20x plus 5 over the divisor of 3x squared minus 7x. So that was a bit disappointing. So why don't we call that maybe A? And let's do another one because that was not the best long division example. Again, I'm doing ones, but I want to do ones that we can't use synthetic division for. So let's go ahead and do, this one doesn't look terrible. So let's say we have 6x cubed plus 2x squared plus 22x, and we're dividing by 2x squared plus 5. This one's a little interesting because we're missing the x term in the middle here, and we don't have a constant term on top, so we need to account for both of those things. So it kind of depends how you like to write it. Again, I'm going to write 6x cubed plus 2x squared plus 22x plus 0. And then if you're really particular, you could even write 2x squared plus 0x plus 5 on the outside, just to reinforce the fact that you don't want to miss that 0, that x term that should be appearing in the divisor. So again, I'm looking at 2x squared and how many times that can go into 6x cubed. That would be 3x, and then I multiply it through, I'll get 6x cubed plus 0x squared, let's say, and then plus 15x. And then this is what I want to subtract. And when I subtract it, I'll be left with 2x squared, and then 22 minus 15 would just be leaving me with 7x, and then I could bring down my 0 just to account for everybody. The 2x squared's already matched, so I just need to do a plus 1, because 2x squared times 1 is going to give me 2x squared plus 0x plus 5. And again, I want to subtract this entire polynomial, so I'll end up with a 7x, 7 minus 0, 0, and then 0 minus 5 is going to leave me with a minus 5. So that's going to be my remainder. So my 6x cubed plus 2x squared plus 22x divided by 2x squared plus 5 leaves me with a 3x plus 1, the numbers on top, and then I have my remainder 7x minus 5, which is divided by 2x squared plus 5. And that is that. So that's it for division of polynomials. Like I said, for the most part, we'll be able to use synthetic division because usually we'll be asking questions about, find the remainder, or is this a 0, in which case you can determine that by just using synthetic division. That amounts to dividing by a linear factor. If you do have to answer some questions about true long division, you would do it this way, where it's just step by step, and you want to pay attention to all the exponents of x and that they're lined up properly. So if there are missing terms, you want to make sure all the degrees are appearing there, and just add those leading zeros for the terms that are missing, and that way everything will be lined up, so you shouldn't miss anything as you go through the division process. But anyway, that's it for dividing polynomials. This is Dr. Lennon signing off.